Hello guys, welcome back. In the previous video, you have seen that we have done pre-processing and cleaning on the text, and now we are going to learn how we can convert that text into meaningful numbers for our machine learning algorithms to understand. So for that we have NLP techniques, and we have three kind of NLP techniques. One is the bag of words, another one is the TF-iDF, and then word to vec. So in this video we are going to learn about these two techniques, bag of words and TF-iDF, because that is what we are going to use in our modeling part as part of this series. And word to vec, I'll create another video so that you can understand how word to vec works. So let's come back to the bag of words. So bag of words is a very simple process where, let's say, you have two sentences. Sentence 1 says the sun is shining, and sentence 2 says the rain is pouring. Now you can see that we have some unique words, and the sun is shining 4, 5 and 6. Here you can see that we have 6 unique words, right? So we will have a dictionary where we will have 6 unique words. So let me write down these 6 words. The sun is shining, rain and pouring, right? Now you can see that we have some words which are occurring more than once. So we will create a dictionary where we will have the values also. The is coming 2 times, sun is coming once, is coming 2 times, then we have shining 1, rain 1 and pouring 1. So how bag of word works is we replace these words in the data with the frequency. So that is why it is also called as count vectorizer in sklearn, because it works on the frequency of the words. So let's see one example of this bag of words. So if you want to import the bag of words, you will have to import this count vectorizer from sklearn feature extraction.txt, and this module will give you the count vectorizer. And now I have some sample sentences here. So we have, in the state of art NLP field, embedding is the success way to the resolve text related problems and outperform bag of words, and all these words are there. Now what I'm gonna do is I'm gonna import this count vectorizer in an object which is count vect here, and I will use this count vec to fit and transform on this complete document. So what is this fit and transform? I will explain in a while, but just imagine for a second I am going to convert this whole text into its frequency, which I have shown in the example earlier, right? So I will just run this cell, and now you will see that this count underscore occurs will hold the frequency, and this count vec, which is here, the object, will hold the features, the words in distinct words. Alright, so what you can see here is I have created a data frame from these two things. One is the frequency and another one is the words, unique words, which are the features in count vec. So, and I have given the columns word and count, and if I run this cell, you will see that all these words here are, I have printed first few words using head, right? And you will see the frequency. So off is coming 3 times, as you can see, once here, then once here, right, and once here. Similarly, if you see other words like BOW, bow, it is coming once here and then it is coming once here. So this is how count vectorizer works. It has converted the words into its frequencies. So let us see another example. Like I have declared a corpus here with different sentences, and I have used count vectorizer in an object vectorizer, and again I am doing fit underscore transform on this corpus, and then you can see you can call this get feature names with this object and you will get all the words that are there in this corpus. As you can see, all the words are there in one list. Let us see the count, the frequency, which is we have stored in this X part here, right? I am converting this X to array so that it can be displayed here, and you can see that all these words have corresponding frequencies for each sentence. For example, and is occurring 0 times in first sentence, right? That's why it is 0 here. Document is occurring once, you can see this, so that's why it is 1. Similarly, if you see this second sentence, you will see that document is coming twice. That's how it is replaced with 2 here. Similarly, if you see this second sentence and the third word, which is first here, because these are the features and features will remain in this shape and only the numbers will change in the sentences. Alright, so if this word is not present in that particular sentence, it will be 0 there. Alright, so that's how simple the bag of words it is. So again, there is one more example here with n-gram. So you can also pass n-grams to the bag of words. So what is going on here is I am giving n-gram range 2,2, which means that it will only take words with 2 words. It will only consider 2 words together as one word. For example, all these words, if you see here, have been collaborated into 2 words. For example, and this is now one word. This is now one word. Is now one word. So these kind of things is important when you see in life. We have, for example, a company name Tata Consultancy Services. Now Tata Consultancy Services, these are 3 unique words, but individually they don't hold any value, right? They don't represent the organization, but together these 3 words come together to represent an organization. Another example is Birla Soft. Birla, a different token, different word. Soft is a different word, different token, and both have different meanings, right? But together they form a unique entity. That's where n-grams comes into play. So if I give the range n-grams range from 1 to 2 here, you will see that my single words and the double words are both are included. So you will see that is the, right? Document is, all these things, range becomes 1 to 2. Similarly, if I give range 3 here, you will see that my feature size is getting increasing again and again, because it will take all the permutation combination from range 1 to 3, right, in the series. So you will see that and this is. So that simple is the bag of words to understand, but it has its own limitation. Here you can see that the construction of sentence doesn't play an important role, right? It only works with the unique words. It doesn't take care of the construction of the sentence or the grammatical expression of the sentence, and a lot of limitations are there. That's why we now come to the point where we use TF-iDF. So let's move on to the TF-iDF. So in TF-iDF we have 2 things, TF and IDF. In NLP, we have few terms like this: turn frequency, document frequency, and inverse document frequency. So what is turn frequency? Turn frequency is the, let's say for turn frequency of word X, is the count of word X in a document, divided by the total number of words. Alright, this is what this formula is saying. Now what is the document frequency? So document frequency is the total number of documents that contains the word X. That is why it is denoted by DFX. So X is the word, okay, and the total number of documents that hold X. Now inverse document frequency is similar to document frequency, just that it is the log of the total number of documents divided by the document frequency. And the TF-iDF will come out to be this TF that we calculate here and IDF that will calculate here, multiplication of both turn frequency into inverse document frequency. So the whole idea of TF-iDF over bag of words or count vectorizer that we have seen earlier is simply that the words that are present in abundance will have higher TF, right? Their turn frequency will be higher, like the, is, are. These are conjunctions or determiners that is majorly used for the construction of the sentence and does not hold any much impact, right? Any much meaning to the sentence. So that can be normalized, that turn frequency can be normalized using IDF. So in IDF, the words that will be in abundance will have lower value. Let's see this with an example. So let's say I have two documents here. Document A holds the rain is pouring. Document B holds the rain has stopped. I will just tokenize those words here. And you can see in bag of words A, I have the tokens of this document, and in bag of words B, I have the tokens of document B. So now the unique words will be the union of both, which is what I have taken here, right? All the words are there in this unique words. And now what I'm going to do is I'm going to create a dictionary with the count of words. So you can see this is kind of a turn frequency where the is coming once in the document A, so that's why it's 1 here. Stopped is coming 0 times, it is not present, that's why it's 0. And similarly it will be for B here. So what is happening here, I am just counting the words and creating a dictionary. Now my whole idea is, first I need to know the turn frequency for all the words, then I will calculate the inverse document frequency. Once I have both, I will just multiply them. So in turn frequency, what I am going to do, I am just simply passing this dictionary and all bag of words. So bag of words simply is all the words, right? So what happens in compute TF, it is just I am counting these words, and once I have passed this number of words, this dictionary and all the words of A. So let's compute this and see that TF of A, turn frequency of A, which is the document A, the is having the turn frequency of 0.25. And you can also see that here the is coming once, right? And the total number of words are 4. So 1 divided by 4 is 0.25. So nothing much. Now what happens in compute IDF? It will be the log of, so I will just show it now. It will be the log of total number of documents and the total number of documents the word contains, which is what is present in the variable well here. Now I am not going on all this logic. I will quickly show you how the output would be. So if I compute the IDFs, I will have to pass the same things again. And you can see the IDF of the is 0. And you know that the was coming in both the documents, right? You can see here the is coming in both the documents. So n is equals to 2. The total number of documents are 2. And document frequency of the will also be 2, right? So 2 divided by 2 is equals to 1, and log of 1 is 0. That's why you can see here the value of the is 0. So similarly it has gone for all the words. And now if I just show you without the log, you will be able to relate it better. Now you can see that for the it is without log it is 1, and with log of 1 is 0. Similarly for all the words. Now that is what I have done here. I have just removed the log function. So now that I have both turn frequency and inverse document frequency, what I am going to do is I am going to compute the TF-iDF, which is what I am doing here. I am computing that I am multiplying the TF, term frequency, into inverse document frequency of that word, and similarly I am passing the values here, and when I will call the function. And now you can see that turn frequency of document A, turn frequency of document B, and then print the data frame. You can see that my words like the, which were coming in both the documents, and rain, which were coming in both the documents, their value is now 0, right? And the words, important words like pouring, stopped, and has, all these words will hold the value. So just like in document 1, the stopped is not present, that's why it is 0. Its TF was 0. And in document 1, the IDF of the was 0. Similarly, that's why it is 0, 0, 0 for 4 words and in again document 2. So what happens in TF-iDF is simply you give more weightage to those words that are rare. What happens in count vectorizer or bag of words, there was no such criteria where you will give weightage to the rare words also, but the words that are present in most abundance will hold the most weightage. So that's why we have gone for the TF-iDF. And now if you want to apply the TF-iDF, you just have to use the TF-iDF vectorizer. So just don't worry about all the code that I have done here. Just import the TF-iDF vectorizer from sklearn.featureextraction.txt, and then you can apply this on our data, which we have it in the data title. All right, and I will run this, and now you can see my vectors is a sparse matrix, right? If you just want to quickly see the all the words, what you can do is you can use this vectorizer, paste here, and then print get feature underscore names, and you will see a list of all the words present in the complete corpus. So there are two more things in TF-iDF. One is this data title. If I just show you a glimpse of this, it needs the complete sentences, as you can see here. Okay, so we have pre-processed the sentence earlier, right? We did it here, as you can see. So what I have done is I have just, instead of getting the tokens of sentences in the data frame, I just converted those tokens into the sentences again by joining them with a space. All right, so nothing much. You just want to give the complete sentences and it will automatically tokenize those, so you don't have to worry about this. And the second thing is this fit underscore transform. So you might want to know what is this fit underscore transform. So basically if you just do fit, it will create the dictionary, a dictionary like this that we have created here. Okay, and then each dictionary, as you can see here, holds a position. The is having the 0th position, stopped is having the 2nd position, right? And once the dictionary is created, you will do the transform, wherein transform your features will be created, your TF-iDF values will be calculated. So if you do this thing on test data, right, that we will be doing in the next video, we will be doing only transform in the test data, because we want to follow the same dictionary pattern, right? We don't want the positions of words to be different than what I have done earlier. So this is it in the feature extraction part. So what we have done is we have just computed the vectors for the complete corpus of my title, and now I'm going to use these vectors in my modeling. See you in the next video.